For over a century, our power grid relied on the physical momentum of massive spinning metal turbines. Coal, gas, and nuclear plants generated electricity by rotating these giant iron machines in perfect sync. But today, we are dismantling that hardware. We are replacing that spinning iron with inverter-based resources, or IBRs. These are massive fields of solar panels, wind farms, and industrial battery storage facilities. They don't rely on synchronized moving parts. They use solid-state electronics to push power onto the grid. Because these new resources inject power digitally, they interact with the grid's frequency differently than analog machines. When multiple digital controllers react simultaneously, they can generate chaotic electrical waveforms that collide with the main power supply. These are subsynchronous oscillations. Left unmanaged, these oscillating frequencies can ripple through the network, creating voltage spikes that physically damage grid equipment. If a severe oscillation trips protective relays, it can cascade into a widespread blackout. This is a document published by NESO, the National Energy System Operator. It outlines their direct countermeasure to this threat, the version 2 guidance on oscillation assessment for inverter-based resources. The rulebook sets a specific mandate. Before any new renewable plant is allowed to connect to the national network, its developers must perform mathematical proofs showing their electronics will actively damp or absorb these stray oscillations, rather than amplifying them. NESO uses this framework as a specific engineering filter. It creates a technical baseline that every new project must meet to ensure the modern electronics powering the nation contribute to system stability. Because developers cannot run risky oscillation tests on the live power grid, they must build a digital twin of their proposed facility. This is an electromagnetic transient, or EMT model, a simulation that replicates the exact software, hardware, and communication delays of the physical plant. Depending on the plant's size and connection type, NESO assigns a specific battery of tests. These simulations are run under stressful, minimum short-circuit conditions, testing the facility when the grid is at its weakest and most vulnerable. The first mandatory assessment is the step change study. This acts as a sudden physical jab to the system. The engineers simulate an instantaneous jolt to the grid's voltage or phase angle, like dropping the nominal voltage by 5% in a split second. The software watches how the digital plant reacts to that jolt. To pass, the resulting oscillation must stay under a 5% peak-to-peak threshold, and the entire system must absorb the shock and settle completely in under 2 seconds. When an inverter-based plant clears this hurdle, it proves it can take a sudden disturbance on the network and rapidly return the local grid to a stable baseline. Next comes the small signal injection study. This schematic shows how engineers continuously pump a range of artificial frequencies, from 1 Hz up to 100 Hz, directly into the simulated AC grid pathway. This graph illustrates the goal. The taller black wave is the voltage oscillation running through the grid without the renewable plant. The shorter red wave shows the plant's software in action. The facility acts as an electrical shock absorber, compressing and damping that wild frequency. Engineers compile the results into a ratio graph, comparing the voltage magnitude with the plant against the magnitude without it. Because the blue line stays beneath the red dotted threshold, it confirms the plant is shrinking the oscillations across the targeted frequencies. Clearing the small signal injection sweep confirms that the hardware won't blindly bounce chaotic frequencies back into the network. It will actively scrub the noise out of the grid. The third assessment is the most detailed: active frequency scans. Instead of testing a single pathway, engineers use a multi-input, multi-output, or MIMO approach. This maps how the plant's total electrical impedance interacts with the network across multiple variables. This generates a massive volume of data. The simulation runs current injections, analyzing frequencies from 1 up to 500 Hz to create a 3x3 matrix of impedance magnitudes and phase angles. To analyze how these 9 variables interact, engineers calculate the eigenloci of the system, effectively mapping its characteristic stability markers onto a Nyquist plot. For the plant to pass, this sweeping curve must stay clear of a specific coordinate, -1 and 0. If the line loops around that point, the math indicates the system will spiral into instability. The final mandatory check is an eigenvalue analysis. This is a pure mathematical cross-examination of the plant's control loops. It calculates the raw damping coefficient, verifying that all possible oscillation modes naturally achieve a damping ratio of at least 10%. These assessments move from physical jolts to layers of abstract frequency mapping. Together, they provide a mathematical framework that significantly reduces the risk of hidden digital interactions causing a total grid failure. Running the simulations is only the first step. Developers then compile the output into automated reports, providing traceable time domain plots in the appendices so NESO can verify the math. This data-driven modeling marks a shift from the analog era. Previously, the raw physical momentum of spinning turbines naturally covered up many electrical imperfections. As we scale up renewable projects, this software compliance gauntlet becomes the essential bridge. It ensures we can transition to a green grid while maintaining measurable technical standards. NESO's V2 guidance provides the technical guardrails needed for this transition. By identifying and mitigating oscillations before a plant goes live, it ensures the shift to an inverter-based grid is built on a foundation of measurable stability.